Hi, in this second video we're going to talk about other undetermined forms that we can obtain where we're doing limits. Consider that we have a limit when x goes to a, and we have a multiplication of functions, and where that multiplication of functions is going to have one of the limits going to 0 and the other one going to plus or minus infinity. So you're going to have a situation where you have a 0 times infinity undetermined form. You cannot resolve what 0 times infinity is, and so we need to recast the limit in a way that this is a shape of the way 0 over 0 or infinity over infinity. Now, a similar treatment can be approached when we have limits that give indeterminate form from the shape 1 power to infinity, 0 power to the 0, and infinity power to the 0, as they can be essentially recast to a form 0 times infinity. And then those recast to something of the shape 0 over 0 or infinity over infinity. So the procedure is assume for anything that is from the shape 1 power to the infinity, 0 to the 0, or infinity to the 0, you gotta assume that the limit is gonna have one of those shapes. Then we're gonna have that the limit is somehow a number L once that we apply logarithm to it. So we're just saying, hey, L is going to be the limit when x goes to a of g of x ln of f of x. And then this limit now can be put in the form of 0 over 0 or infinity over infinity. Essentially, we're applying the logarithm to this type of limit, and that's going to give us one of these different indeterminate forms. Then, when we get that, we apply the L'Hopital's rules again, and then when we obtain the limit, then we apply exponential to the limit, and we're going to have back or original limit. Okay, so let's see some examples of that in action. So first, we're going to have limit when x goes to infinity of x squared times sine of 1 over 4 x squared, right? And so notice that this limit is clearly infinity times 0. 1 over 4 x squared goes to 0. So this is something of the shape infinity times 0. So we do a recast. And so the way that I can do this is essentially, notice that having x squared here is the same that having 1 over x squared dividing. This is an algebraic manipulation where we're essentially putting a fraction over here, and notice that this is x squared by this and 1 times 1. So with this algebraic manipulation here, notice that this is kind of similar to the shape sine of u over u, right? I just need to introduce 1 over 4 here, and it will be the same. So I can see this as 1 over 4 on the top, limit when x goes to infinity of sine of 1 over 4 x squared over 1 over 4 x squared as well. So now notice that this is 1 over 4, and this limit when x goes to infinity of this can be thought about like limit when u goes to 0 of sine of u over u, and we've seen that using normal L'Hopital's rules, this gets to be 1. Okay? When x goes to infinity, then 1 over 4 x squared goes to 0, and that's the replacement that I'm doing here, just in case. So I change the variable of the limit, and this just is going to transform 1 over 4. But the L'Hopital's rule is what is behind solving this final limit. So this is the first one here. Now another indeterminate form that is going to show up is in this case where we have a subtraction, we have limit when x goes to infinity of x minus x squared minus 3x. And so notice that this is like infinity minus infinity, so it's very difficult to manage. The best way that we can approach this is probably still doing some conjugate about it, since I don't have a way to multiply or do anything special with it at this point. And so I get this and multiply by x plus this, up and down. And so the next step we're going to have is still x squared minus x squared minus 3x over x plus square root of x squared plus 3x. Now let's see if this actually gets to simplify a lot. I think this is going to still produce an undetermined form of the infinite over infinite form, because here we're going to get x squared cancel with x squared, but we're going to have 3x on the top, and then we're going to have x plus x squared plus 3x. So this is still infinity over infinity. And now we can apply L'Hopital's rule here. And if we apply L'Hopital's rule, this is going to be 3, and this is going to be 1 plus, and then this is going to be 1 over 2 square root of x squared plus 3x. And then by the chain rule, this is going to be 2x plus 3. Okay. And now this is not going to be an infinity over infinity form. Actually, the top is already not going to infinity. And the bottom is neither, I think. I think these two are linear terms. So it's going to be kind of difficult to find out right away what it is. So I'm going to have 2x plus 3. And I'm going to have to divide by x here. And I'm going to probably have to divide by x here. But we're going to divide by x with the square root of x. Square root of x squared, which is essentially x. And so let me expand over here. So this becomes limit when x goes to infinity of 3 over 1 plus 1/2, and then this part becomes 2 plus 3 over x, and then below this becomes the square root of 1 plus 3 over x as well. Since I can combine this whole root, x squared divided x squared is 1, and 3 over x over x squared becomes 3 over x. Now when x goes to infinity, this goes to 0, this goes to 0, and this transforms into 3. 1 plus 1/2 times 2, and this becomes 1, so it's just going to be this, 3/2. And so as you can see, this is also combining a lot of algebra with leaning to having different undeterminate forms. So now let's go back to another example. Now we have limit when x goes to 0 by the right of x power to the x. And so this is one of those limits that I'm going to have to call L, whatever this is. And then I'm going to apply log on both sides. So limit when x goes to 0 of log of x power to the x is going to be equals to the log of L. And so for now, I'm going to forget about the log of L. So I can continue doing the limit. But then this is going to be limit when x goes to 0 by the right of x log of x. And notice that this is now a 0 times infinity situation. 0 times infinity situation. And so I need to recast this as infinite over infinite, or 1 over or 0 over 0 form, it's much more easier to recast it as a infinite over infinite. I'm going to switch this x to be 1 over x dividing. Remember, this is just essentially me getting back on the way that I can fold this fraction. This is log of x over 1 over x. If you multiply the streams over the middle, it gets back to be x log of x. Now, if I do L'Hopital's rules here, then this is going to be the limit when x goes to 0 of, and the derivative of log is 1 over x, and the derivative of this one is going to be minus 1 over x squared. So I got to be careful here because I can potentially continue doing infinity over infinity, but over here, instead of doing more L'Hopital's rule and getting bigger powers, I can just simplify with the fraction and multiply top with top, middle with middle, and I'm going to have minus x squared over x. And so this is the limit when x goes to 0 by the right of minus x, and this is just 0. Okay? But at this point, I got to remember that this is the log of L, right? So the log of L is 0, so the exponential to the log of L is equals to the exponential of 0. And so L is just going to be 1. And so that implies that the limit when x goes to 0 by the right of x power to the x is just 1. Another example of this would be limit when x goes to infinity of 1 plus 1 over x power to the x. And so notice that this is shape 1 power to the infinity. And then I can probably assume that this is going to be some limit r instead of being 1 to the infinity. And I'm going to apply the logarithm again. So log of r is equals to the limit when x goes to infinity of x log of 1 plus 1 over x. I'm trying to cut the steps, but essentially putting down the power once that I plug in the log. Now notice that this is an infinity times 0 situation. And so I do need to do the recast again. Or essentially rearrange this, but you know the trick at this point, which is dividing by the x that is multiplying. So this is 1 over x here. And of course, this is now a 0 over 0 situation. And so I can do normal L'Hopital's rule. And by L'Hopital's rule, this is limit when x goes to infinity of 1 over 1 plus 1 over x. This is the derivative of this log. Now by the chain rule, which is going to be minus 1 over x squared. So this is just the derivative of this one here. And then minus 1 over x squared, the derivative of 1 over x. So now, as you can see, I can cancel out some terms. And this is going to be the limit when x goes to infinity of 1 over 1 plus 1 over x. This goes to 0, and so the limit overall becomes 1. And so now, because the log of r is 1, so r means that is e to the 1 or e. And so that means that this limit at the top really was the exponential to the 1 or the Euler number. Right? So to finish up, notice that the last two examples can kind of be seen graphically. We have the function x to the x, and we can see here that when we're approaching 0 by the right, this is kind of going to 1. So if you plot this in like Desmos or the calculator, you can kind of see where this function is going when you're approaching 0 by the right. And so you can kind of tell, oh, okay, this should go in this direction. Similarly with 1 plus 1 over x power to the x, you can see that that's kind of going to the Euler number as an asymptote when x goes to infinity. And this is a good tale sometimes, or a good approach when you don't know if a limit is what it's supposed to be. Just make a graph and try to see where the things are going, where the limit is going when you're trying to calculate that limit. Now, another important thing to take into account when you're calculating this type of limits with indeterminate forms is that you can compare growth rates. And so if f and g are functions that they're both going to infinity, then you can kind of check who's growing faster. So you can say f grows faster than g if when you're going to infinity, the limit when x goes to infinity of g of x over f becomes 0. Or equivalently, if the limit when x goes to infinity of f over g is infinity. The dominating factor is gonna go to infinity, and if the dominating factor is at the top, then the limit is infinity, and if the dominating factor is at the bottom, then the limit goes to 0. Now, sometimes what happens is that they have comparable growth rates, so they're growing at the same pace. So for example, when I had like a square root of x squared plus 1 and the linear function 3x minus 1, those two things are order linear, and so they have comparable growth rates. And at that point, what's going to happen is that the limit when x goes to infinity of f over g is going to be equals to a certain constant. Okay? In general, the ranking growth of rates as x goes to infinity is something that you can see comparing the order of magnitude of the functions. So for example, the logarithms is the bottom of the barrel, and after that you have the powers. Then the powers by the logarithm grows faster than the single power, but of course you can make that be outgrown by another power with a bigger exponent. And of course powers are overtaken by exponential with a particular base, and of course a variable power to the variable is going to overtake a fixed base exponential. So this is like the order of growth and the ranking of growth. And you can kind of see this here on how powers are going to overtake lines, and how, of course, exponentials are going to overtake different powers. So this is the end of section 4.4 in L'Hopital's rules. Make sure to continue watching videos on the practice of this topic.